Okay, so welcome to part three of this series. The series is on state machine, and we are looking into more state machine. So, to understand this completely, you need to watch part one and part two. That will give you the example that we are looking into, and we are creating a traffic controller. Last time we stopped here on this table. So we understood this state machine diagram, and we also look into this one. What we really have to figure out is this combinational circuit, because and then this combinational circuit. This combinational circuit will determine the values of LA and LB. And this combinational circuit is going to determine the value for S prime. Now we already figured out that S prime, okay, actually we didn't figure out. Let's start with here. Okay, we know TA is a single bit, TB is a single bit. Remember, TA, this sensor and this sensor, they're sending the same signal. All they're sending is, okay, whether there are students or people standing here, what the same we need to make on this thing. Okay, so you can think of this thing. Let me do that. Yeah, this and this, they are connected together as one signal, which is coming in here, and then this one and this one coming together as one signal here. So what happens is, based on TATB, this one, we need to decide about S prime. So we need to decide about what state next is. But you know that, okay, this is just a symbol, S1, S0, S2, S3. We need to have some sort of bits here. And next question is how many bits we need. This flip-flop can be n number of bits, any number of bits. Total, how many states we have? 1, 2, 3, 4. So in order to represent 4 states, we need 2 bits, because 2 bits can have maximum value, maximum number of values as 0, 0, 0, 1, 1, 0, 1, 1. So we can represent S0 with this, S1, S2, S3. So now we have figured out is, okay, if I do, let me take a look at another. So S0 is 0, 0, S1 is S2. By the way, this is prime, okay? This is this is 2 is 0, so I'm following this one. 0, 0. And these values over here, which are S prime, they can have these different values. They also depend not only on the inputs, but they also depend on the current state, so value of these ones. So let's, a state machine, we decide whether it is prime. Prime is only the only thing it's telling this prime is the next state, but actually these will be the same. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, let's do the same thing for this one. 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. There's 3 here, there's 2 here, there's 2 here, 1 here. Okay, you understood this one? So now a good portion of this truth table, everything we have in a binary format. So we can determine the value of S. So there are 2 bits. Okay, so in an actual, there will be 2 bits. So this will be called S1 prime, this will be S0 prime. Similarly, this will be S1, S0, and they will have a circuit here, and both this one will go back and this one will go back. So in other words, now what you can do is this one is S1 prime, this is S0 prime, this one is S1, this is S0. So all we have to do is we have to determine when S1 prime is 1, inputs are these two and these two. Similarly, we have to determine a digital circuit for S0 prime, which is this one. So now this problem goes back to where we started combinational circuit, truth tables, determining the Boolean equations, creating a very simple circuit for each one of those. Then we will get to that. So we will determine this. I think from here problem will be simple. But let's look into the other one. What do we need so that we can complete this whole table with the binary numbers? So this combinational circuit, on the input is need S. So it is dependency on this one. So we have already in binary format. But it needs to generate outputs, or it needs to generate actions. And LA and LB. So one second, let me maybe take this one. So this light and this light will have LA, we call light A. And then this one and this one will have one shared signal, because when you want to turn this on, this will be on, and this off, this off. So we don't need to generate two separate signals. We can connect them and bring LB. Okay, now let's look into LA. So LA needs to make red, yellow and green. Three different values, three different unique values. If it's 1 bit, we can have only two unique values, 0 and 1. But in order to do 3, we need at least 2 bits. The same like this, we will have 0, 0, 0, 1, 1, 0, 1, 1. We don't need fourth. We will use only these. So what we do is we say for green, when it's green, let's make it a little bit, we do 0, 0. And for yellow, I'm gonna use orange here because it's easier to see, 0, 1. And then we need 1, 1, 1, 0. What that means is when we want these two lights to be green, we need to send 2 bits. So first of all, this is a 2-bit signal. All right. Or in other words, we will have two signals for LA and 2 bits for LB. So it will be bit 1 and bit 0 of LA. Similarly for LB, we need bit 1 and LB bit 0. Same signal name, but it will have 2 bits. Or we can also have one line and say it like this. Whatever is easier. We need to have, what we need to have here is, let me make sure on my next page all right, yeah, I use the same value. All right, actually, let's come here. This completes everything. You can set off me drawing over there and it's messing. So you have understood, right? We have to determine the binary values of everything. We have these symbols, so we have binary, and we already have binary, and for these ones, using this scheme, or I should say using this scheme, we have determined. So LA, let me get this signal over here because this is an important. Bring it over here. All right. Now let's look into LA. Is green? Green means 0, 0. 2-bit signal. LB is red, means 1, 0. Follow this thing. Similarly, it's same, orange 0, 1, red 1, 0. And that's how everything is. Now this whole truth table is complete. Now if you ask me what were the outputs. So these are the oops, open. These are outputs. Okay, what else? Inputs. These are the inputs. Yeah, what else? Then these are the current state. These are internal values over here that we need to determine, and this is also internal value. I hope you understood this one. Can be a little bit overwhelming when you're doing first time, so I suggest if you don't understand, stop it here, go back to this video or previous videos, start with part 1, part 2, part 3, try to understand everything, and it's very simple. And the beauty is that you will be able to create a practical digital circuit for a practical application. Okay, that is done. So what do we need to do next? What we need to do next is, let me remove these colors because I might be using this. All right, so next is we need to determine the output. They are dependent on this current state, and then we need to determine next state, which is dependent on this and cancel, and that's what we're gonna do next. Now comes the fun part. Let's do it for the next state. Let's bring this guy over here. Where should I put this one? Let's put this one. Can I put this over there? Yeah, just for a reference. Sorry for it, it's a little bit smaller. So the very first thing is over here, S prime, and S prime has S1 prime and S0 prime. So let's do S1 prime, and if you create this S1 prime, it depends on what inputs, TADB, and then it depends on this current state, which is S1, S0. So I'm creating a K-map. Again, if you don't know what K-map is, I did a video on it in the combinational part. So please search that video, and in a few minutes you will understand the whole thing. So what we're doing is, again, going back to the combinational circuits, wherever the values of 1, we are determining combination of the inputs and current state that will produce 1. And this is sum of min terms. But if you look at this table, this is your task. Maybe you should stop it and go and try to do it so that if you remember K-map or not. So S1, S0, we go with 0, 0, 0, 1, 1, 0. Every time 1 bit changing, same thing here. I'm not going into too much K-map. So just fill this table based on this. So this one, whenever S1 is 0, S0 is 1. So look at this. For this combination and this combination, doesn't matter what values we have. Look at that. When it's 0 and 1, so let's look into 1. When input S1 as 0 is 0, 1, doesn't matter what TATB, output will be, S1 prime is 1. Similarly, when it's 1 and 0, doesn't matter what values of TATB, it really will be 1. That's it. And these two. So if you can even look at from this one, if you did a combinational circuit, that we have this S1 prime is 1 when S1 is 0, S0 is 1, or S1 is 0, S0 is 1. And you can look at from the K-map too. These ones, when you put them in one group, the only thing that changes are these two. And you know that, what is this? Exclusive OR gate. So S1 prime is just exclusive OR of S1 and 0. So all you have to do is, for S1, 0, we will just put this gate. Okay, let's do S0 prime. S0 prime, I'm going to do same example. I'm not going into details, so you need to do that based on the the combinational videos that I did. So you fill the K map like this. So you can only make grouping here, but not for this. So you will have three terms. Those are the three terms. You can simplify here because S1, S0, TB dash, they are common. So you are left with this one. We had a theorem on that. A number of complements and plus itself becomes 1. So we had this one. So eventually, well, when you go down to S0 prime, this is your circuit. So job done for this and this. And how current state is always on a rising of the clock. You take value from here to here. So we don't need to determine that. Next thing to determine is really here. And let's do that here. So let's first the most significant bit of LA1. It becomes 1 here, 1 here, 1 here, and that is the scenario for 1 0 1 1 1 1. So LA1 is really, but if you see that whenever S1 is 1, it is 1. Whenever S1 is 0, is 0. You can make a K map, it should show the symbol, but this is a pretty simple observation. So the LA1 bit, basically when it's connected to S1, it's really S1. Now LA0, it's all 0 just for this combination. For 0 1 combination, it's 1. See? So 0 1 means S1 is prime, S0 is 1. So how I write in this equation, I've already covered in combinational part. So if you don't understand, or if you jumped onto this video directly, you really need to have some basic knowledge how these minterms are calculated, and so you need to watch the combinational part. LB1, simple. It feels like is S1 but inverted. So when S1 is 0, it's 1. When S1 is 1, it's 0. So you see that? LB0 is only this part, which is when both S1 and 0 are 1. So if I map that, LB1 is simply connected to S1, LB2 is connected to these two in AND gate, LB1 is inverted form, LB2 is this. Alright, so you understand that one? My video is getting a little longer, but that's okay. I want to do another video on this one. So what we're doing now, okay, now this picture that all along was with us, and we were determining this. So we figured out S prime over here. So we have two bits because the states are 4, so we need 2 bits. S1 prime, S0 prime. S1 prime, we already figured it's with this gate. And keep in mind this S1 is connected to this one. Here I'm not showing a connection from here to here. But current state, I created a normal version as well as the inverted version, because sometimes we need S1 prime. So what we do is simply connect this one here. S0 prime, we simply connect this one here. So it's better to have these two, because these two are also determined this one. So these two are already the two S1 prime and S0 prime we already calculated here. This one. And they're connected to inputs, and the same thing input. I need to create an inverted form. Actually, the only inverted forms I used. On LA1, on the output side, we have 4 bits, 2 bits for each. And these were the gates we previously figured out here. And based on that, they need to be connected to this. Here in this picture, I'm showing complete actual connection. Actually, I don't want to show it on the above one not to make it look messy. But here you can see all the connection are written. Let me leave it here. I think everything we have already done. So this whole circuit is a controller that we can use. So I'm leaving the screen as is, so you can take a snapshot of look at it. When you do your own calculation, you can compare with this one. And if I made a mistake, please let me know. That's it. All right, that's all I think. But the overall, if you step back higher level, Our controller, let's say our controller is somewhere here. Somewhere here and closer. This is our controller, and it's sending these signals LBLA, and it's getting inputs from this and this, and it's getting a clock, and it's getting a reset signal. And we can put this box somewhere closer here maybe, and have relevant wires go somewhere to these everything. All right, I hope I explained it well, and if you still have questions, you can send me email, you can text me on LinkedIn, and I will be happy to answer any confusion. Okay, thank you so much. See you next time. Bye.